Welcome to this week's lecture. So, in the previous week, you have seen the introduction of process. You have already know what actually process is in operating system and how processes are stored in the operating system. And in this lecture, we will discuss about process scheduling. So what is process scheduling, or why does process scheduling is needed in operating system? So as you know that the task or the job of the operating system is to execute processes in the computer, right? So all the processes are stored in the memory, and those processes comes from memory into the processor of the operating system, and the processes are executed there in the processor. So as there are a lot of processes, a numerous number of processes in the operating system, so this is a mandatory task to identify or to make the decision that which process will be executed at which time. I mean, you need to make a schedule of the processes that are in the operating system. So what actually is scheduling? See, if there are these 5 processes and these 5 processes are ready to be executed, I mean, and they wants to be executed right now, but in your processor, if your processor is single core processor, then not more than one process can be executed at a certain time, right? So out of these 5 processes, which process should come first, which process should come second? In this way you should make a schedule. So if we see, this is the CPU and these are the processes, then there can be many sequence of processes. Many sequence of processes can be possible. Say for example P1, P3, P2, P4, P5. This is a sequence of processes, and P1, P2, P3, P5, P4. This is another sequence of processes. So we can say there are two schedules. Either the system or the operating system will follow this sequence of processes or this schedule, or the operating system will follow this schedule. So that means you have to have, I mean the operating system should have or must have the schedule of the processes that the CPU will follow to execute them. Okay. So as we have discussed about schedules or scheduling, that means the processes that are available in the operating system, they will make a queue, and we have seen an example in this slide that this is a queue, right? P1, then P3, then P2, then P4, then P5. This is a queue. So, and this queue is actually called or is recognized as scheduling queues in operating system. So in the operating system there are many scheduling queues, and in these queues the processes actually waits to be executed. So ultimately these queues actually stores the processes in different steps of the operating system, and different queues are maintained in different steps. You know, the processes follows some steps to be executed, right? In the normal stage the processes are stored in the memory, in the secondary memory. Then those processes comes into the primary memory, and then from the primary memory those process goes to the processor or the CPU. So the processes actually pass several steps to be executed ultimately. So the first type of queues is job queue. Okay, so job queue, actually this queue is situated or resides in the secondary memory, and it keeps all the processes of the system. So in the job queue all the processes are stored, and this is actually physically situated in the secondary memory of the operating system or the computer system. Then comes the ready queue. So ready queue actually resides in the main memory, or you can say the RAM of the computer, and it keeps all the processes that are waiting to be executed. I mean, from the secondary memory or from the job queue, the processes comes into the primary memory. I mean, the processes comes into the ready queue, and from ready queue actually the processes goes to the CPU to be executed. So here we have seen that two kind of queues. One is job queue and another is ready queue. So job queue is situated in the secondary memory of the computer system, and ready queue is situated in the primary memory of the computer system. And then there's another kind of queues that are device queues. I mean, you have multiple devices in the computer system, right? Say for example, that can be a monitor, that can be secondary storage device, hard disk. So these are the resources or other devices connected with the computer system. And multiple process may require the same device. Okay, right? So if multiple process requires the same device, but the device itself, it cannot serve more than one process at a certain time. So what will happen? So some process, maybe P1 is currently executing these devices, but other processes, P2, P3, they also need this device, but this device is currently hold or currently occupied by process 1. So what will happen to P2 and P3? P2 and P3, this process actually cannot proceed further unless they get this device 1. So what will happen? Actually they will form a queue, that P2 and P3, they actually need device 1. So when P1 release device 1 after using this, then P2 and P3, they will get the device. So in the meantime, P2 and P3 are waiting somewhere, right? Where actually they are waiting? They are waiting in this device queue. So device queue is another kind of queues that are available in operating system, and in these queues those processes actually wait here who actually wants to use this device. So for every device there is a dedicated device queue in the operating system. So basically these are the basic type of queues that are available in the operating system. Okay, now we can see the queuing diagram, or we can say the scenario or the lifespan of a process. Okay, so a process comes to the ready queue from the secondary memory, or we can say hard disk drive. So from the secondary memory the process comes into the ready queue, and from this ready queue actually the process goes to the CPU to be executed. Okay, if the process is done with its execution, I mean the process is finished or the process has completed its task, then the process will be terminated and go out of the CPU. But the process in its execution time may require many things, many resources, or the process itself may be interrupted. Okay, so what can happen when the process is executing in the CPU? One thing can happen is the process is requesting for an input-output device. I mean, during its execution, the process is currently in need of a device, or in need of an input-output from the user. So what will it do? It will make a IO request, and when it makes an IO request, it goes to the IO queue or input-output queue. Why? Because your input devices or output devices may be occupied by other processes, right? You don't know that. The process itself doesn't know that. So at first the process goes to the ready queue, and if the IO device are available, then the process gets the IO devices and it comes out of the IO queue. But if the IO devices are busy or occupied by other processes, then those processes actually waits here. Okay, so after the process is done with the input output, then it again goes to the ready queue to go to the CPU again. Okay, so this is one scenario. Another scenario is that time slice may be expired. What does it mean? Whenever a process comes into the CPU to execute, the process doesn't execute there for indefinite time or for infinite time, right? So the process are given a slice of time slice, or a specific amount of time to be executed in the CPU. If that time is passed, or that time allocated to the process is expired, then what does it do? The process again comes out of the CPU and again goes to the ready queue. Another scenario is the process itself may create a child process of its own. Okay, so fork a child mean in Unix system actually creating a new process, or creating a child process of this one. So when a process P1, this process actually creates a child. When it creates a child, so it goes out of the CPU and the process actually waits. Why does the process wait? In the Unix system, whenever a process creates a child process, the process waits until the child executes. So when the child process is done or is finished with its execution, then the main process, that P1, again goes to the ready queue to start its execution or to resume its execution. Okay, so and another scenario can happen. That scenario is that this process is waiting for an interrupt. I mean, this process is expecting that some other process or the system will interrupt its execution. It is required for in some cases. So the process actually waits for an interrupt. I mean, the process comes into this queue and wait here until the interrupt is occurred. So when interrupt occurs or interrupt is done, then the process again goes to the ready queue to start its execution again. So this queuing diagram actually represents how a single process in its execution time can be can stop or can pause its execution and can go out of the CPU and wait in some other queues for some event to occur. Okay, and if those events are done, or if those events are occurred or finished, then the process again goes to the ready queue to resume its execution. Okay, so we have discussed about scheduling, and we have discussed about the queues that actually holds the processes that are scheduled. So to make the schedule, or to make that which process will come first, which process will come later. So there are many schedulers in the operating system. These schedulers actually makes the schedule of the operating system. So what kind of schedulers are available in the operating system? So there are mainly two type of scheduler. The first one is the long-term scheduler, and the second one is the short-term scheduler. So what does the long-term scheduler do? The long-term scheduler actually picks or selects process from job queue, I mean from the secondary memory, and bring them into the primary memory or the ready queue. So the job of the long-term scheduler is to select processes from job queue and bring them into ready queue. On the other hand, the short-term scheduler actually selects process from ready queue which are already in the primary key, and selects the process to be executed, I mean to go to the CPU. So this is the job of the short-term scheduler. So short-term scheduler actually are executed more frequently than long-term scheduler. So that is why actually they are named as short-term scheduler. Why they are executed more frequently? Why do you think? See, just in the previous slide we have seen the queuing diagram. I mean, you have seen that the process comes to the CPU from ready state or ready queue, and the process actually comes out of the CPU for other events to occur. That can be creating a child or an interrupt or whatever that is. They may be, the process can be brought out of the CPU for other events to occur, and when those events are occurred or finished, then the process again goes to the ready queue and again goes to the CPU. So in this way actually the process moves from ready queue to CPU and CPU to ready queue. So if I say that some process, say for example P1, P2, P3, these processes are in the ready queue, and these processes actually goes to the CPU and comes out of the CPU, again goes to the CPU and again comes out of the CPU. So ultimately, to finish its execution or to terminate the process, if we think about a single process P1, let us think that P1 needs 10 seconds of CPU time to be finished or to finish its execution. But in the first time it goes into the CPU and spends 2 second time, and then goes out of the CPU maybe for some input output, and whenever that input output is done, then the process actually again goes to the CPU and maybe spend 5 seconds, and then maybe for some other event the process goes out of the CPU and goes to the ready queue, and after those event is done, is finished, then the P1 again goes to the CPU and spends 3 seconds. So see, to finish its execution, P1 comes to the CPU 3 times and goes out of the CPU 3 times. So I mean the process have moved among these two 3 times. So after moving, after swapping here, or swapping 3 times, then P1 is finished or P1 is terminated, right? So short-term scheduler worked 3 times here to pick P1 from ready queue to CPU. But if we think about the long-term scheduler actually picks process from job queue to ready queue only then if there is any empty space in the ready queue. So when there will be empty space in the ready queue, if a process among these three is finished its execution. So when P1 goes out of the ready queue, I mean it's finished its execution, then only the long-term scheduler selects one process from job queue and brings that into ready queue. I mean long-term scheduler works one time. So now you can see the differences. The short-term scheduler actually executes more frequently. I mean the task of this scheduler is very frequent, and the task of this scheduler is comparatively less frequent than the short-term scheduler, right? And if you think about this, that the short-term scheduler first worked after 2 seconds, then worked after 5 seconds, then again worked after 3 seconds. So the time spent or the interval is very short, right? But the long-term scheduler, it actually worked when the whole 10 seconds is finished here, right? So the interval here for the long-term scheduler is larger. That is why actually this scheduler is called long-term scheduler. And another thing is, this long-term scheduler actually controls the degree of multiprogramming. What is the degree of multiprogramming? The degree of multiprogramming means that number of process that can be stored in the ready queue. We can say that. So the degree of multiprogramming is the number of processes that can be situated or that can exist in the ready queue at a certain time. So if we say that the degree of multiprogramming is fixed, in this example the degree of multiprogramming is 3 because there are 3 processes in the queue. So long-term scheduler actually maintains this degree of multiprogramming. Why? Because it doesn't load or it doesn't actually bring process from job queue to ready queue at its own will. It only brings the process here only if there is empty space in the ready queue, right? So in this way we can say that long-term scheduler actually controls the degree of multiprogramming in the operating system. So the processes are actually mainly of two kinds. Some processes are CPU bound and some processes are IO bound. So what does it mean? CPU bound processes spend more time doing computation using processors than input output, and on the other hand IO bound processes spend more time in input output than doing computation in the CPU. So what does it mean? We can think of an example. Say if you write a program that is a calculator program, so in the calculator program what does you do? Where you actually takes input from the user. You take two numbers and then you print the summation or subtraction, addition, multiplication, whatever the user wants. So in this process actually the computation is very less. If the whole program executes for 5 seconds, maybe 1 second is required for the computation, I mean the addition, multiplication, those things, but other 4 seconds are actually necessary, are actually spends for the user to give input from the keyboard, right? So that means this process is a IO bound process. Why? Because maximum execution time of the process is for the input output, not the computation. Okay. And if we think about another process, say for example you have written a program. That program will find you all the prime numbers, all the first 1000 prime numbers. Okay, so that means the whole program, all the whole code what you have written, that uses the CPU, the processing power of the computer, right? That means it uses the computation to find the first 1000 prime numbers. So this process is a CPU bound process. So there may be different kind of processes in the operating system. Some are IO bound and some are CPU bound. So the goal of the operating system is to optimize the resources of the computer system. So to optimize the resources of the computer system, the operating system should choose a specific amount of CPU bound process and a specific amount of IO bound process. So who actually does this? The long-term scheduler actually does this. So the long-term scheduler must select the process wisely so that all the process doesn't be CPU bound process, and all the process are not IO bound process. So the long-term scheduler must select wisely. Why does the long-term scheduler must select wisely? What will happen if all the processes are IO bound? What will happen? So if all the processes are IO bound, I mean, say for example there are 5 processes in the ready queue and all the processes are IO bound. What will happen? The processes will come to CPU, and from CPU they will go to IO queue. All the five will come here because all of them will need IO devices, but only one of the processes actually can be served by these IO devices, right? Not all the 5 can be served at parallelly. So one process will be served here and the other 4 will be waited here. So think about the scenario. You had 5 processes in your ready queue, and all the processes actually needs input output device, not the CPU. So all the processes will be stuck here. I mean, will be in the waiting stage in this queue. So what will happen to the CPU or the processor? CPU will sit idle, I mean, because the CPU has nothing to do, right? So if all the processes are IO bound, then the CPU will be empty, or the ready queue will be empty, because all the processes will be queued in this IO queue, not in the ready queue, right? Okay. So the result is empty ready queue. Then again, what will happen if all processes are CPU bound? So what will happen? So if all processes are CPU bound, say for example all these 5 are CPU bound, so this process will come from ready queue to CPU and will be executed here, and this process actually doesn't need IO queue or IO devices, so those processes actually doesn't come to the IO queue. So one process executes here and other 4 waits here. So when this one goes out, then from the left 4, the leftover of this 4, another process comes here. So in this way the execution goes on. No process actually comes to the IO queue for IO devices because all are CPU bound. So if all the processes are CPU bound, what will happen? This IO queue will be empty because the processes doesn't need IO devices, right? So if all the processes are CPU bound, the IO queue or waiting queue, we can say this is a waiting queue. This waiting queue will be empty. So that is why the long-term scheduler must select the processes very wisely, so that the ready queue and waiting queue or the IO queue doesn't stay empty all the time. Okay. And then there are another kind of scheduler, that is medium-term scheduler. So this type of scheduler are very common in time sharing system. So what actually the special feature of this scheduler? The feature is swapping. So why the swapping is required? Swapping actually reduces the degree of multiprogramming in the operating system. Sometimes it is useful to reduce the degree of multiprogramming. So what actually happens here? Everything is similar like normal execution, but here in this case there's a special scenario, which is that at a certain time the processes which are in the primary memory, I mean in the ready queue, and they goes to the execution in the CPU, those processes can be swapped out of the memory. I mean those processes are swapped out of the primary memory, and those processes are sent back to the secondary memory, and in the secondary memory they actually create a queue. So in this queue, which processes are stored or are waiting? The partially executed swapped out processes from the CPU. Those processes are actually form a queue here in the secondary memory, and after some time these processes can be brought back into the ready queue. So this is called the swapping, and this swapping actually is integrated in the medium-term scheduler. Medium-term scheduler can do this type of activities, I mean can do the swapping to reduce the degree of multiprogramming in the operating system. Now we have seen that the processes goes to the CPU, and then it comes out of the CPU, and in the meantime another process, that process comes to the CPU. So the CPU is executing different process in the different time. It loads a process, it executes the process, and after some time it loads another process, right? So this is called actually context switch. So when an interrupt occurs in the operating system, the system needs to save the current context or the current state of the process that is currently executing in the CPU. So context switch actually is composed of two steps. In the first step, what does it do? It stores the currently executing process's context, and the second step is it restores the next process that is to be executed. Okay, so if we see this diagram, see in the first time process P0, in this time process P0 is executing, right? In the this blue line actually represents the execution. So the process P0 is executing, and at a certain time the CPU thinks that this process should be stored, should be stopped, or should be paused, and another process P1 should start executing. So what does it do? The operating system saves the state, I mean up to which P0 has executed those state. The operating system saves that state into the PCB of this process, I mean process P0, and then the operating system or the CPU loads the PCB or the process state of P1. So from this information of the PCB of P1, the CPU can execute process P1. So it takes some time, I mean to save the state of P0 and then to load the state of the PCB1 or P1, process P1. So it requires some time, that is the black portion of this timeline, and then after this time the CPU actually starts executing process P1. So this time, this idle time, in this time CPU actually doesn't execute any process. CPU spends this time to save and to reload another process. So this time is overhead to the operating system, because in this time CPU is idle, right? So this is an overhead in the operating system. And then again, if we follow the timeline, you can see that the process P1 is executing, and after some time the operating system decides, or the scheduler decides, that P0 should start executing again. So to start P0 executing again, what does the operating system do? It stores the currently executing P1 into PCB1, and it reloads the content of P0 up to which it was executed. So it reloads the information from the PCB0. So again a context switch is occurring, or is happened here. So this context switch, these times, these are overhead to the operating system. So the goal, or the motivation of the operating system designer is to design such an operating system which actually reduces the overhead for the context switch in the operating system.